Hi, and welcome back to Codex. Today's speaker is Nathan Johnston from Mount Allison University. Professor Johnston is an expert in quantum information theory and related problems in matrix analysis and convex optimization. Today, he will tell us about a new formula for the determinant. Take it away, Nathan.
All right. Yeah, thank you very much for having me. So I'm Nathan Johnston. I'm located at Mount Allison University, which is a tiny little university in New Brunswick, which is a tiny little province on the east coast of Canada. So yeah, hi everyone. So today I'll be talking to you about the determinant of a matrix. Don't worry, no quantum information theory or anything like that. Just back to basic linear algebra. We're going to learn some stuff about the determinants. And so the way that I like to think about the determinants it's a multilinear form. So we can think of it as a tensor. We can think of it as a tensor living in, well, if f is whatever field I'm working over, then I can think of it as a tensor living in Fn tensored with itself n times. If you don't know what tensors are, don't know what any of that means, don't worry about it too much. So, sort of the reason for doing this is to, I want to make precise the notion of how many terms there are in a formula for the determinant. Okay, so back in intro linear algebra, you probably learned a formula for the determinant that involved a sum over permutations, and it had n factorial terms in it. And I just sort of want a way of making that precise so that I can sort of precisely talk about the number of terms in a formula. And this is my way of doing it. So anyway, when I think about the determinant as a tensor, it has this formula here, and this just comes from that usual Leibniz formula that you learn in intro linear algebra. So here, these e's, these are standard basis vectors. This means the vector that has all entries equal to 0 except a 1 in the sigma 1th entry, where sigma is a member of the symmetric group. It's one of the n factorial different permutations on n symbols. Okay. And yeah, it just comes from the usual Leibniz formula. So when I think of think of the determinant as a tensor in this way, I can ask questions of it like I can ask questions of any other tensor. So for example, I can ask, what is its rank? What is the rank of this tensor? Okay. Anyway, so for example, this should be a determinant, 2 by 2 determinant up here. This is the n equals 2 case. This determinant tensor, what it looks like if I write down this previous formula a little bit more explicitly. So this formula that we saw here, if I write it out a little bit more explicitly in the n equals 2 case, well, it's just E1 tensor E2 coming from the identity permutation minus E2 tensor E1 coming from the transpose permutation. And I mean, that's just exactly equivalent to writing down everyone's favorite formula for the 2 by 2 determinants. Okay. And okay, so I started asking questions about this tensor, this determinant tensor in general. And for example, I can ask, what is its tensor rank? Okay. And what that means is, what is the smallest sum that I can use to write down that tensor? Okay. What is the least number of terms that I can use to write down the determinant tensor as a sum of elementary tensors, is what these are called, where it's just something tensored with something a whole bunch of times. That's an elementary tensor. Okay, and the question is, what's this minimal R? In other words, what is the tensor rank of the determinant? Okay, so for example, I mean, when n is 2, when you're talking about the 2 by 2 determinants, this formula right here shows that the tensor rank is at most 2 because there are 2 terms in this sum. Okay, more generally, I mean, this sum here that we saw on the very first slide, well, there are n factorial members in the symmetric group. So this sum has n factorial terms. So the tensor rank of the n by n determinants, it's at most n factorial. Okay, so this is very standard, sort of starting point result for us. Okay, so that just comes from that defining sum or the Leibniz formula for the determinants. Okay, so for example, yeah, the 2 by 2 determinants has tensor rank 2. Somewhat surprisingly, the 3 by 3 determinant, your first guess would probably be tensor rank is 6, right? Because it's 3 factorial is 6. Everyone's favorite formula for the 3 by 3 determinants, it has 6 terms in it. But it turns out you can do better. You can write down a formula for the 3 by 3 determinant that only has 5 terms in it. In other words, the tensor rank is at most 5 because of this funny little decomposition here, okay? And there's sort of a standard way, if you don't like this tensor decomposition stuff, there's a standard way to turn this into a formula for the determinant of a 3 by 3 matrix that's it's like A12 plus A13 times A11, or sorry, A21 plus A23 times A31 plus A, the tensor which tensor factor it is tells you which row of the matrix you're taking entry from, and then the subscript on the standard basis vector tells you which column of the matrix you're taking an entry from. So anyway, this is a formula for the 3x3 determinant that just involves 5 terms. And if you sort of combine this with things like cofactor expansions, then very quickly you get a nice upper bound on how large the tensor rank of the n by n determinant can be. That's better than the naive upper bound. That's better than n factorial. Actually, for an n by n matrix, you can write down an explicit formula for the determinants that's no larger than roughly 5/6 to the power n over 3 times n factorial. So a little bit smaller than n factorial. Okay, so I mean, this result down here, and I believe this decomposition here, they're not horribly old. They're, I don't know, maybe 10 years or so. Certainly no older than that, I don't think. But anyway, yeah, so that's from Harm-Dirksen. And then our result is sort of a continuation in that direction. Okay, it's a better upper bound. It's a better upper bound on the tensor rank. Okay, so our result shows that the tensor rank of the determinant, it's less than or equal to the nth Bell number. Okay, so I'll talk more specifically about exactly what that means later. But for example, when n is 2 or 3, you get these bounds of 2 and 5. You recover these best known bounds that we already have. And actually, this 2 and the 5 for the 2x2 determinant and the 3x3 determinant, we know that these are optimal in this case. So like we of course couldn't hope for an upper bound. We know equality is attained in these 2 cases, and sort of our bound matches those 2 known values. But our bound is better than the previously known bounds for n bigger than or equal to 4. In particular, if you compute the ratio of our bound bn to the previously known bound, the Harm-Dirksen bound, you get something that's going to 0. So it's quite a bit better than was previously known. Okay, it's still not right though. Okay, for example, when n equals 4 or 6, then very recently there's another paper posted by Kim and Ju, where the 4th Bell number, so our 4th Bell number for the n equals 4 case, our upper bound is 15. Okay, which again, so like the naive bound is 24, right? 4 factorial. Our bound is 15. Well, Kim and Ju, they showed that actually 12 terms suffice. You can write down a 12-term formula for the 4x4 determinant, and they get a similar improvement in the n equals 6 case. They improve our 203, the 6th Bell number, to 180. They also, they get another formula, their formula works for any values of n, but it's only better than ours in these 2 particular cases. Anyway, so the tensor rank, that's one way, sort of at a high level, the reason that we like the tensor rank, one way of thinking about it is it sort of measures, in some sense, the complexity of the tensor. It's like how much junk is going on in that tensor, just like the rank itself for a matrix. It sort of describes how complex that, or how complicated that matrix is, how much stuff is going on there, how non-degenerate that rank or tensor is. And so the tensor rank is one way of capturing that. But there's another notion of rank as well, and we're going to look at that. There's something called the Waring rank. Okay, so I'm going to build up to another notion of rank as well now. It's a little bit different, but sort of has the same high-level idea. Okay, and to sort of do this, I'm going to sort of shift focus. I'm going to think of the determinant now as a homogeneous polynomial. I'm going to think of it as taking in n squared variables, right? The n squared entries of your n by n matrix, and it's some polynomial in those n squared variables, which again, it's just the polynomial that pops out from you doing the usual Leibniz formula stuff, sum over permutations and products of matrix entries. Okay, so this is a homogeneous polynomial, and for any homogeneous polynomial, you can ask what its Waring rank is, and what the Waring rank is, it's kind of like a way of measuring how much interaction there is between the different variables or something like that. It's like how many cross terms there are, or how complicated the cross terms are, or something like that. So again, it's the least number of terms that you need in a certain sum, but this time what the sum is, it's, linear combinations. So these CKs are just scalars here, and these LKs, these are linear forms in the same variables. Okay, so these LKs, these are linear forms, and I'm raising them to the nth power, which I've kind of got to do if I want this thing over on the right to have the same degree as this thing over on the left. Okay, so it's the least R for which I can write the determinant as a linear combination of nth powers of linear forms. Okay, that's called the Waring rank. And so a bit of a mouthful. Let's start with the 2x2 case. So when n equals 2, Well, the determinant, it's a homogeneous polynomial in 4 variables, 4 entries of a 2x2 matrix. And well, it's everyone's favorite formula for 2x2 determinants. And well, okay, I claim that the wearing rank is at most 4, and a way to see that is this funny little decomposition here. Okay, if you were to expand out all this crap here, it would simplify down to exactly this expression up above. And hey, this is the sum of squares of linear forms, and it has 4 terms in it is the point. So wearing rank is at most 4. Okay, and again, the question is just, well, like in general, what's the fewest number of terms that you can use in a decomposition like this? What's the fewest number of powers of linear forms that you can use in a sum to get the determinants? Okay, and this sort of thing here that we're doing here, like sort of where this comes from is this first term, x11 times x22. We're sort of splitting that up into 2 sums of squares. These first 2 terms here are giving me this first term, and these second 2 terms here, they're just sort of designed so that like the x12 squared and the x21 squared, those will cancel out, and all that'll be left will be the cross term. All that'll be left is this one right here. And you can do this sort of thing in general. And when you do this, when you sort of like, when you say, okay, I've got a tensor rank decomposition of the determinant, and okay, I'm going to take every single one of those tensor rank many monomials and split them up into a sum of powers of linear forms. Well, each one you can split up into 2 to the n minus 1 linear forms. Okay, so in general, like this, again, like this is sort of a standardish result. The wearing rank of the determinant, it cannot possibly be larger than 2 to the n minus 1 times the tensor rank. Okay, so in some sense, yes, like we're going to get new bounds on the wearing rank, but they just sort of come for free from this. We're really going to get new bounds on the tensor rank and then just use this fact and get stuff for free. Okay, so yeah, so for example, at one point in time, not too long ago, the best known upper bound on the wearing rank was just 2 to the n minus 1 times that tensor rank upper bound from Harm-Dirksen that we saw a bit ago. And then it was improved by Johns and Tytler about a year ago, I think, to n times n, maybe 2 years, I don't know, a year and a half, somewhere in there, not too long ago. It was improved to n times n factorial. And well, our bound that we get is just 2 to the n minus 1 times the nth Bell number, which actually kind of sucks when n is small. But then when n is bigger than or equal to 17, if we do a similar sort of thing to what we did before, where we compute the ratio between our upper bound and the best known previous upper bound, well, it goes to 0. So we get a better upper bound on the wearing rank when n is bigger than or equal to 17 as well. Okay, so all that we've got left to do is to see where this upper bound on the tensor rank comes from. Okay, so what is this new formula for the determinant? Why does it have, I don't know, Bell number many terms in it? And so on. Okay, so all right, so let's do that. All right, so the standard formula for the determinant, it's a sum over a combinatorial object, right? It's a sum over permutations. It's a sum over the symmetric group. And our formula, it's going to be sort of similar in spirit. It's going to be a sum over a combinatorial object, but a different one. It's going to be a sum over what we call partial partitions, okay? So these are similar to partitions, except we don't require that every single member of sort of the big set be a member of one of the parts, right? Okay, so for example, like if n is 5, well, a partition of 5 would be something like 1, 2 in the set, and then 3, 4 in the set, and then 5. That's an example of a partition. You're just grouping the numbers 1, 2, 3, 4, 5 into disjoint subsets. And a partial partition, it's the same thing, except, you know, it's okay if you miss some numbers. Okay, so for example, a partial partition of 1, 2, 3, 4, 5 would just be 1, 2, and then 5. And well, 3, 4 didn't make an appearance, but who cares? Okay, it's just a partial partition, so that's okay. If the union of all the parts is the entire collection of numbers 1 up to n, then it's just a regular partition. And we're going to be particularly interested in the partial partitions that have no singletons. So we're going to look at the partial partitions that don't have something like this, that don't have just a set or a part with just one member. And we're going to denote those partial partitions with no singletons by pp of n. And well, one really nice fact about these partial partitions with no singletons is that there's a nice bijection between them and the partitions themselves. Okay, so for like the way that it works is, okay, if I write down all the partitions and then just erase all the singletons that I see. So I erase the set containing just 3, just 2, just 1. Then I get exactly the set of, all the partial partitions with no singletons, okay? And that is a bijection. And I mean, this tells me right away how many partial partitions with no singletons there are, because it's sort of a well-known counting thing that the number of partitions is the nth Bell number. Okay, so that's where this tensor rank bound is going to come from. We're going to be summing over these objects over here on the right, and how many of them are there? Well, there's the same number as this many, which is the nth Bell number. Okay, so partitions themselves give you equivalence relations, right? If you partition, the set of integers from 1 up to n, then you can say that 2 integers are equivalent under this partition or this equivalence relation, if and only if they're in the same part. And well, what we're going to do with partial partitions is we're going to do the same thing. We're going to think of 2 integers as being equivalent. If they're in the same part, it's not an equivalence relation anymore, though, because it's okay if down here, because it's okay that some numbers are missing. This equivalence relation is not actually an equivalence relation. It's not reflexive, okay? Numbers aren't necessarily related to themselves anymore. But other than that, it's I don't know if there's a name for this. It's still transitive. It's still reflexive. Or it's symmetric and transitive, but not reflexive. I don't know what that's called, but equivalence relation, but a little bit worse. Anyway, okay, so we're gonna think of it kind of like an equivalence relation, though. Okay, and then yay, big beast of a theorem time. We'll try to get our heads around this a little bit, but anyway, yeah. So here's the theorem. So you have, some matrix over whatever field you like. N by n matrix, then the determinant, it's a sum over, instead of being a sum over permutations, it's a sum over partial partitions with no singletons. So, right, so there are Bell number many terms in this sum. And the sum, in some sense, is very analogous to the usual Leibniz sum for a partition, right? We kind of have this sign here, which is kind of like, it's very analogous to the sign of a permutation. The sign of a partial partition, like the way that you can think of it is, okay, if I go back here to these example partial partitions, what the sign of a partial partition is if I were to think of this partial partition as a permutation written in cyclic notation, okay? So for example, I identify this partial partition up here with the cyclic permutation 1, 2, 3, right? It says 1 to 2, 2 to 3, 3 to 1. Well, that's an even permutation, so this is an even partial partition as well. Okay, down here, I identify the partial partition 1, 2 with the permutation written in cyclic notation as 1, 2. In other words, just transposes 1 and 2. Well, that's an odd permutation, so this is an odd partial partition as well. Okay, so I'm going to give it like sign -1, whereas this even one up here, it had sign +1. Okay, so that's all this funny little sign function down here is doing. Okay, this part's maybe a little bit different. Okay, it's the, the size, you take the size of each part and you do compute the factorial of their size. So there's not quite anything analogous to that in the original formula. And this junk over on the right, it looks a little bit more complicated than in the usual, sum of permutations formula, but it's sort of very similar in flavor, right? Like what's going on here is like you fix a row and then you're summing over members in that row, okay, right? And then you product together all of those different formulas for each row. So it's sort of very similar in spirit to the formula to the usual sum of permutations formula. Maybe other than that, I'm going to not focus on the details much at this point. But if you sort of work through all the hideous details and write down what this formula gives you, for example, in the n=2 case, for 2x2 matrices, it just gives you exactly like the usual formula. Okay, so nothing different happens in that case, right? For n=2, there are 2 partial partitions with no singletons. There's the partition that contains everything, and there's the partition that contains nothing, and those correspond to these 2 terms here. Okay. And then for n=3, you can ask, okay, what happens in this formula here? And well, this time we have 5 partial partitions with no singletons. And if you go through all this ugly junk here and write down what formula you get this thing right here. Okay, this is what that previous formula was in the n=3 case. And this is, it corresponds very naturally to exactly that tensor decomposition that we saw a couple slides ago. The fact that, this tensor rank decomposition involving just 5 terms. This is that tensor rank decomposition in some sense. Okay, and then the formula still works for higher values of n as well. Okay, and each of these 5 terms here, I mean, these just correspond to these 5 partial partitions here. The first one and the last one, those are even. Okay, so they have plus sign in front of them. These 3 in the middle, these are all odd, so they get a minus sign in front of them. And yeah. Okay. And yeah, so I don't know, like in some sense, this isn't any better than anything that was already known, because we already knew this formula for the 3x3 case, but we didn't know sort of how to properly generalize this to 4x4 and 5x5 and so on previously. So hey, here's a formula for the determinants of a 4x4 matrix. If you do things sort of the normal sum of permutations way, you're gonna have a formula with 24 terms. This one has 15 terms. I mean, sort of the trade-off is that the terms are more complicated, but because we're sort of encoding this precisely in terms of tensor rank, it is an improvement in that sense over what was previously known. Okay, so previously tensor rank 24. I think the bound, if you use Dirksen's funny little formula 5/6 to the power of floor of n over 3 times stuff, I think that gave you a formula of 20 terms. I think that got you an upper bound of 20, and then here here we have 15 terms for an upper bound of 15 on the tensor rank. And this is the first time where we actually get coefficients other than +1 or -1 in front of some of the terms. You can see we've got 2's here. And the reason for that is when n equals 4, that's the first time that any of your parts, that's the first time when you're going to have more than one part. Okay, this time when n is bigger than or equal to 4, there are some partial partitions with no singletons that have 2 parts. Right, so that gives you a 2 factorial in the formula here, which gives, you know, so like one of these 3 terms up here corresponds to the partial partition that has like 1, 2, and then 3, 4 in separate parts. One of them corresponds to the partial partition that has 1, 3, and 2, 4, and the other one corresponds to 1, 4, and 2, 3. Okay, and those are the only partial partitions in that case that have more than 2 parts if they have no singletons, or at least 2 parts if they have no singletons. Okay, all right. So yeah, this formula, it's a bit of a nightmare. It's kind of awful and whatever, but so let's talk about where it came from so that maybe you can build up a little bit of intuition for what the heck's actually going on here. Right, okay. So let's see. How do we introduce the determinants to our students back in our intro linear algebra classes? And I don't know if you're anything like me, you do a little bit of geometry. You try to motivate it to them geometrically. The determinant, it measures, areas of parallelograms or parallelepipeds, or rather signed areas of, or signed volumes of parallelograms or parallelepipeds, right? You think of it as a linear transformation, and it takes a square or a cube or whatever, and it turns it into a parallelogram, and you're measuring the signed area or volume of the output of that. So it sort of gives you this picture on the left. Okay, if I have a matrix that has columns 5, -1, and -2, 3, then I plot those vectors, make a parallelogram out of it, and the determinant tells me the signed area of this parallelogram. Okay, and if I wanted to, I could take this parallelogram and just sort of tile the plane with it, right? And I mean, like we do this when we think about linear transformations geometrically. We imagine like sort of the unit square grid getting deformed into a parallelogram grid. Okay. Well, so this gives me a lattice on 2-dimensional space. What I'm going to do is sort of focus on these 4 corners of this parallelogram here. Okay, and what I'm going to do is I'm going to make a different tile that tiles space on this exact same lattice. Okay, it's not going to be a parallelogram anymore. The advantage of this new tile that I make over here on the right, its advantage is that its sides are all going to be parallel to the coordinate axes. Okay, so what I'm going to do is I'm going to make this funny little L-shaped thing right here. Okay, and the reason for doing this is, okay, so first off, the area of this funny little L-shaped tile, it's got to be the exact same as the area of this parallelogram on the left, because they tile space on the same grid. Okay, so like I don't know, you can do like a limiting argument where you take a big region and you say, oh, how many tiles are in here, and you compare areas, and you find out that the area of this L-shaped tile is got to be the same because it's on the same grid. Okay, and furthermore, I mean, this L-shaped tile here, you can compute its areas sort of rather directly, because you can compute what all these coordinates are, and everything's sort of nice and rigid and aligned with coordinate axes. If I didn't have this funny little inlet at the top right here, if it was just a rectangle that went all the way over like that, then the area here would be A times D. It would be the top left entry of the matrix times the bottom right entry of the matrix. It would be A11 times A22. And then how much did I take off? Like, what is this little corner piece that's missing here? Well, that's in the 2x2 formula for the determinant, that's like the A12 times A21 piece. Okay, we've subtracted out this rectangle that has area A12 times A21. Okay, so like we can sort of think about like that's why, like in one sense anyway, that's why the formula for the 2x2 determinant is, you know, AD minus BC, because it's a big rectangle with AD, with area AD, minus a small rectangle with area BC. And well, the same sort of logic, it works in higher dimensions as well. It's just a lot uglier and sort of harder to get our head around. Okay, for a 3x3 determinant, again, okay, so the usual way of doing this is like we imagine we start off with the unit cube, okay, side length 1 in every direction. We apply our linear transformation, our matrix to it, that turns it into a parallelepiped in 3-dimensional space, and we talk about the signed area of that parallelepiped. That's the determinant. Okay, well, that parallelepiped gives us a lattice in 3-dimensional space, and I'm going to construct an axis-aligned polytope that tiles space on the exact same lattice. Okay, and the way that we do it is, well, the tile is going to look something like this, which I don't know, it's kind of weird and a little bit harder to picture. But the point is, again, like it's axis aligned. All these sides here, they're parallel to one of the coordinate axes. So it's really easy to write down, hey, what is the volume of this thing? And well, one way to compute that volume is, well, it's the volume of the big enclosing rectangular prism minus sort of a big rectangular prism at the front, and then 3 smaller rectangular prisms in the corners, which gives you this funny little shape here. And this is a 5-term decomposition of the determinants. Okay, here's one term, here's another term in the determinant, and here's 3 more terms. And so that gives you the area of the shape, which again, because it tiles on the same lattice as this parallelepiped, it's got, you know, it's equal to the determinant of a 3x3 matrix. And you can play this sort of game in higher dimensions as well, but I suck at visualizing high dimensions. So I'm going to stop with the pictures there. Okay. All right, so everything that I've said so, well, okay, maybe not everything. Most of the stuff I've said so far works over any field. Of course, this stuff here, maybe I'm picturing it in Rn, but okay, let's forget about that. Pretend pictures work over any field too. All right, but now going forward, the stuff I'm going to talk about is going to be specifically over fields with non-zero characteristic, just because we get some better bounds, some better results in those cases. Okay, so if you're working over fields with non-zero characteristics, some really nice stuff happens, okay? So for example, if you're working over a field of characteristic 2, then your tensor rank, it's not just less than or equal to the nth Bell number, you get an actual tighter bound, okay? So the Bell numbers, they grow exponentially quickly, but they actually grow more quickly than that, right? Like there's one of these sort of funny in-between growth rates where it's like, it's quicker than k to the power n for any fixed k, but it's slower than n to the n. It's one of these funny in-between growth rates. So here, when we get an upper bound on the tensor rank, when your field has characteristic 2, when the upper bound is 2 to the n minus n, it's quite a bit smaller than the nth Bell number. If your field has characteristic 3, then we get an upper bound that looks something like this, some weird, you know, involves like a 3 to the power n and a 2 to the power n term, plus sort of a polynomial correction factor. And in general, like if the field is if the field has characteristic p, then you get an upper bound that's something like p to the power n. And where this comes from, is just, whoops, sorry here. There we go. There we go. If we just go back to our formula here, let's see, how's this work? I forget where this comes from. A whole bunch of terms in, if it's characteristic p, then a whole bunch of terms here are going to be 0. Right. I believe it's, ask me about that at the end. Okay, but it's the same formula. It's just a whole bunch of terms end up being 0, and I apologize. I'm having a bit of a brain fart on that. But anyway, so in the p equals 2 case, for example, like we get this upper bound here to the n minus n, which I mean, better results were known for fields of non-zero characteristic previously as well, and this slightly beats these previously known results. So, for example, in p = 2, the determinant and the permanent are the same thing, because +1 and -1 are the same thing. And there are lots of funny low bounds known on the tensor rank of the permanent. And the best one that's field independent that's known, the best one that applies in like this p = 2 case, is a bound by Ryser, which was 2 to the n-1 was the upper bound on tensor rank. So we get a slight improvement. We get, n-1 smaller than that. So slight improvement. In some sense, we don't expect a big improvement because we have some lower bounds as well, right? So like, again, this is also due to Harm Dirksen. He showed that the tensor rank in any field, it's always exponentially large. The tensor rank of the determinant, it's always exponentially large. It's bigger than or equal to n choose n/2. So we don't expect a sub-exponential upper bound in any of these cases. We only expect sort of marginal improvements in that sense. But we can do a little bit better. We're still not sort of honed in completely. So for example, or at least we can do a little bit better again, sort of in this field of non-zero characteristic case. If we sort of focus in a little bit more even now to fields that have q elements, okay, so we let q be a prime power so that there's a field with q elements, then we can get a tensor rank that, okay, again, same lower bound as before, but we can show that it's even a little bit bigger, okay? You get this extra logarithmically sized addition to the lower bound. So we're sort of squeezing in a tiny little bit from both sides, at least, in sort of this special case, okay? And if we try to improve things a little bit more than that, okay, if we sort of hyper focus now, so that now we're looking at the field F2, so the field with just 2 members in it now, okay, so sort of hyper focus as much as we possibly can, and ask, okay, can we get some exact answers here finally? Okay, we've got upper bounds, we got new lower bounds, how tight is everything? And while using everything that we've talked about so far, the best lower bound that we get is 9. So that lower bound there, it just comes from this sort of thing here. And the upper bound is 12, which comes from this formula right here, because field of 2 elements has characteristic 2. All right, so the tensor rank of the 4x4 determinant on the field of 2 elements, it's between 9 and 12. And it turns out, this field is small enough, we can do some exhaustive computer searches to help us find tensor rank decompositions, and it turns out that the tensor rank actually is 12 in this case. So I don't know, mild evidence maybe that the upper bounds are maybe more close to being right than the lower bounds or something like that. I don't know. Okay, so yeah, so we've got these new formulas for the determinant that give us the upper bounds, and I don't know, I like to believe they're pretty good in general, because hey, at least they're pretty good in this case. Okay. All righty. And that's all I've got, so I'm going to stop there. Thanks everyone for your attention, and feel free to ask questions.
All right. Let's everybody hit that reaction button. And I am going to stop.